I guess our next speaker is an invited speaker, Lee Orff, and the one thing that we found out, I think Bill Gallis, I, and Kevin Scow were at the EMS SLS conference in Madison in November, and Lee's presentation really blew everybody away, and we just thought right away we had to have Lee come to our conference and certainly present, because I think you're all going to really enjoy what he has to show and all the cool stuff he has. So we really welcome Lee. Glad he was able to accept our invitation, and I'll give it to Lee now.
All right, thank you very much. First of all, this is my first conference, first Iowa conference, and I wanted to say that I really had a good time, and this is a great conference, and I really appreciate the invite, and I'm very happy to share with you some of my research. I'd like to, of course, acknowledge my collaborators. In this case, we have Rob Wilhelmsen, Bruce Lee, and Kathy Finley. You should certainly be familiar with the last two names there. And I'm going to talk to you about some of the motivation for this work, studying long-track EF5s. I don't have to convince this audience why that's important. Talk about my process, because a lot of it has to do with computing, and then some results. So what we want to do is we want to simulate a thunderstorm that, quote-unquote, naturally produces the most devastating tornado, long-track EF5. And what I mean by naturally, I mean I'm simulating a supercell. I shouldn't have to tweak anything to get it to form. And that's what happens. And then I want to visualize the storm in ways that enable comparisons to field studies, as well as the ability to exploit the fact that we have all the data at all the grid points, and we can see things in the model that we might not be able to see with remote sensing. And then I want to do this for more storms than just the 2011 El Rito storm. Why are we trying to study long-track EF5s? Because while they're the least common, they cause the most damage and the most fatalities. EF4 and EF5 strength tornadoes. Long track, that really doesn't have a definition. I'd say anywhere 20 kilometers or so is like long track. We haven't really defined that yet. The longer the path, the more the damage potential. We really still don't understand why some supercells produce tornadoes, long track, short ones, no tornadoes, etc. Certainly shear and cape, it plays a large role here, especially low-level shear. And in the simulation I'm going to show you, there's an awful lot of low-level shear. This is a composite of 3 photographs from a climatological study looking at cases where there's no tornado, where there's a weak tornado, or a strong tornado for a supercell. And the thing to really focus on is the 0 to 1 kilometer shear. It's very large in these strong tornado cases. And that seems to be a really important factor. And you'll see in the photograph of the storm I'm going to simulate, there's a lot of shear in the bottom, like a few hundred meters. And until recently, we really haven't been able to do this kind of numerical work. We didn't have the computational ability. But now we have machines like Blue Waters, we have machines from the Exceed system that can actually make this work. So what do you need to do this? If you want to decide you want to do this someday, you need a cloud model. I'm using CM1, developed by George Bryant at NCAR. You need the ability to manage an awful lot of data. And this has probably taken up about 75% of my time in the last decade or so, is just managing the tremendous amounts of data that these simulations create if you want to have a lot of very high temporal frequency. And as you'll see from the movies I'm going to make, it looks pretty good. You need a bit of luck, just like you do in the real atmosphere. If you're going to go chase, you don't always get to order your long-track EF5, right? And the same paucity of long-track EF5s is in the model. And that's probably good. That means the model is actually representing the regime pretty well. A lot of computing experience. So if undergrads, graduate students out there, if you want to do stuff like this, you really got to be good at computing, and you should probably like it as well. At Fortran, Python, Linux, Bash shell scripting, video editing software, etc. A lot of patience and a bit of obsession. We're all meteorologists, we're all obsessed with the weather. That problem's already taken care of. So CM1, this is George's definition of the model. It's a lot like WRF without all the extra stuff. And in fact, some of the development that goes into CM1 ends up going into WRF as well. CM1 comes out of the box. If you just download it, you can download this for free. With the ability to exploit these kinds of machines, it uses MPI, a way to distribute communication across distributed memory machines, has OpenMP for parallelizing loops. Some of this stuff may seem gobbledygooky, but it just means that a lot of effort has been put in to make this model work on big machines. CM1 has several microphysics options. We're utilizing the Morrison dual moment microphysics scheme that comes with CM1, and I think it was one of the many factors that had to come into play to make the simulation possible, because of the cold pool temperatures are actually more along what we see in the field. This stuff here, I'll just summarize it by saying you have to pay attention to how you store data, the way you write it, how often you write it, how you aggregate it. What I've been doing here is I'm essentially writing the files, building them in the memory of the machine until I sort of run out of memory and then flushing them to disk. Supercomputers like it when you write really big files and you write them but from a lot of different machines at the same time. So I basically had to do a lot of experimentation to come to a regime that works. So a little bit about Blue Waters. It's the world's fastest supercomputing on a university campus. 13 petaflop peak performance, 1.5 petaflops of memory. It's distributed though. 25 petabytes of scratch, half of an exabyte of tape, about 700,000 cores. Here's, if you look at the nameless.input file for this, it's 2200 by 2200 by 380. It's 1.8 billion grid points. It took a few days wall clock time. There were some fits and starts involved, so I can't say for sure. Roughly 100 terabytes of data to manage. Not just, you have to back this stuff up too. So anyway, what do we do? So I got, from Lou Wicker, he provided me the sounding for this simulation. It's based upon the May 24th, 2011 El Reno storm that Jana Hauser talked about. So in this case, we took a 1 hour rough forecast off the right flank of the storm that produced tornadoes V1 and V2. We triggered the storm using an updraft nudging technique that was developed by Naylor and Gilmore. I won't go into details, but the warm bubble type approach doesn't always work with these storms that have like caps and things like that. Then you do this more than once because it never works the first time. The model blows up, the storm moves out of the box, a million things can go wrong, and then it happens and you go, wow, that actually happened. And then you start showing talks around. And then you visualize the data in a way that makes sense to humans. And I put 3D here because these supercells are inherently very three-dimensional. One of the reasons I like supercells is that they lend themselves well to very nice visualization. That sounds kind of backwards, but I like to make pictures and stuff. All the movies you'll see came from JPEG files or PNG files that were created from software packages. I'm operating on the history data, so once the simulation is done, I'm just going to be hitting that data over and over again. There's two software packages that I've used that I'm very grateful that exist. One is Visit, developed at Lawrence Livermore. It's a supported Blue Waters application. With some help, I developed an interface into my data format so I didn't have to do any intermediate conversions. Vapor is another really good software that I'm sort of pushing to folks who ask me about this stuff. It's a bit like this 5D. It's really great for making trajectories. Whereas Visit, I found I like Visit's compositing ray tracing algorithm. So the movies where you see both cloud and rain are made with Visit, and the trajectories with Vapor. So the storm is a classic sort of merging of an HP supercell. We have a tornado that starts about an hour and a half into the simulation. It's on the ground for almost 2 hours, which is longer than the storm that Jana reported yesterday, the actual storm. There's a lot of interesting things happening between Genesis and decay. There's a lot of, the tornado spends most of its time wrapped in rain, which would be, of course, difficult to observe in the field. Lots of mesocyclones form along the forward flank downdraft boundary. You'll see all sorts of interesting vortex dynamics going on with cyclonic interactions where the two vortices merge together. You see cyclonic, anticyclonic interactions that are destructive. And there's a feature that I'll spend a lot of time visualizing that we're calling the Streamwise vorticity current that is very closely associated with these mesovortices. It also feeds a lot of Streamwise vorticity into the mesocyclone via tilting and likely stretching. And this is what I'm talking about here, and I'll show a lot of stuff like this. This is the forward flank downdraft boundary. Here's a tornado, and there's this air that's just being lifted into the mesocyclone that is helping to drive the circulation aloft. So here's tornado tracks. This is the wind speed up here. Tornado starts here. This is the pressure trace. So keep an eye on these numbers. This is 140 millibar pressure drop when you get into the dark blues, 130 meters per second when you get into the dark blacks over here. So it starts out like a lot of tornadoes do, sort of small and relatively weak. Begins to grow, begins to strengthen. It really begins to start churning along. This feature here is associated with that Streamwise vorticity current. You see a very strong a horizontal pressure gradient that really causes that inflow to be screaming. You can see there's some nice detail here. You see almost these little like cycloidal things going on. You can see the pressure kind of goes up and down. It doesn't always just stay the same. There's this interesting event. It's a very disruptive event that occurs right about here after this thing's been churning along for a while. An anticyclonic vortex sort of sweeps in and gets caught into the tornado circulation and strips away a lot of its vorticity, and it never really recovers entirely from that. Then it becomes more like an EF3 or lower. And this goes on a bit further as well. So it's a long track tornado, very strong. This is the EF5 cutoff, so this is a time series of velocities and pressures. So the dark black line is velocity sampled every 2 seconds near the surface. So we're well into the EF5 range for a long time. If there was an EF6, this would be getting, well, there's not an EF6, so we're not going to worry about that, but it's a really strong tornado. Here's our sounding. We'll focus on the boundary layer in a minute, but it's got lots of cape, lots of shear. It's got a very low LFC. Look at these parameters here. I'll just let them sort of speak for themselves. You see those numbers like that. Somebody from Michigan saw that, they'd probably pass out. Seriously. So there's your LFC, very low, so it's a lot of humidity. Didn't have to lift those parcels too high. Let's go up the sounding here, lift our parcel, look at that big fat cape, go up to the LFC, and you can see where that is up here around 160 millibars or so. Here's our photograph, and here's that really strong screaming shear I'm talking about. So these are meters per second. So this is just speed shear, but the strongest shear you see is like the bottom, gosh, I don't know, a couple hundred meters. That concentrated region of vorticity, I think, is key in some of these long track storms. There's 500 meters a kilometer, et cetera. So you've got lots of cape and lots of shear. Again, it's more complicated than that, but those two parameters are very important. So let's take a look at the storm. So this is a view from the south looking north from afar, seeing the full storm. It looks pretty good. You see your overshooting top. You see maybe the Pleiades cloud there. You see your anvil. You can actually see some evidence of the Mattis clouds when you look really closely. There's actually a tornado and a wall cloud and a hail cloud there. Here's the domain itself. It's 120 kilometers on a side, and it's 20 kilometers deep. And we're using an isotropic grid. That means the grid spacing is constant right in this region of the storm. We're using 30-meter grid spacing. Okay, and that was key too. A lot of times you'll see in models people using stretched grids, but we use an isotropic grid, and I think it really helps the vortex dynamics. So there's our tornado and our wall cloud, et cetera. It just gives you a sense of the scale. In order to resolve this thing, you have to really over-resolve this thing, in a sense. You have to run the whole thing at high resolution. So here I'm trying to sort of mimic what would be a visible satellite image, and obviously they're not blue like that, but you can sort of see some nice features on the top there, make it look kind of nice. So I like to experiment with these different visualization techniques. So here's tornado genesis. This is a box relative view, so the tornado really wouldn't come at you from this direction, but you can certainly see. Here's your tail cloud, and I'll run this back and forth a little bit, show it to you a couple times. It looks relatively good. It looks kind of like a mushroom sort of. These features here are part of the tail cloud. So here's that little anticyclonic guy we keep talking about. This is where the RFD is over here. So it descends to the ground. I mean, it looks like kind of what you see in the field. You see a descending condensation funnel coming to the ground, and it looks reasonably realistic. Here's a view from the southeast looking northwest. Here's that little anticyclonic guy. So here's where you're starting to see the developing wall cloud and the tail cloud. And I'll just let this run for a while. So this is something I visualized with Visit, and it also includes the precipitation field. So here's the RFD, and you see a lot of interesting structure here. The RFD is not really a D, it's a whole bunch of Ds. There's just so many pulsing downdrafts going on. This is kind of a cool place to stop. This is a little rain curtain that forms around the wall cloud. You see these things in the field. It almost looks a little bit like Goshen, but not really. I know you've seen these in radar, these little rain curtains that are maybe 50 meters across. They're probably important. Lots of structure, vertical structure going on in the wall cloud. Blasts of precipitation over here in the RFD. Now this thing's really churning along. You can see the tail cloud. It looks like it's feeding something into the storm. We'll look at this in a little bit. This is just clipping the side of the domain. It's not real. And then blasting downdrafts. I'll be focusing on the temperature of the cold pool as well as we watch this thing, because that's important. You may have heard of the Goldilocks type setup where you have a cold pool that's not too cold and not too warm, and that seems to be really critical. So here it's a rain-wrapped wedge, and it's just, you would not want to be in this region right now. It would be bad, and you wouldn't be able to see what's going on. So I really think this is a good method of trying to convey what it looks like from the field in a reasonable way, so I can talk to storm chasers and we can exchange information. So now I'm going to look at the vorticity field. Here's the storm for reference. You can see what it would look like. But I'm going to be looking at the vorticity magnitude. I'm coloring it by the vertical component. So red means cyclonic, blue means anticyclonic. I'm going to freeze it right here because this is tornado. This is like, pardon the phrase, it's the beginning of Genesis. So this is what it looks like right at the beginning. This is the little vortex that's going to grow into a long-track EF5 tornado. And this is that anticyclonic guy over here. So we just kind of watch. What's interesting and perhaps valuable is it takes 4 to 5 minutes elapses between this vortex genesis and then there, now it's a tornado on the ground. So there's already sort of an anchored circulation in place before you actually see the condensation funnel come down. So at first I was really focusing on what's going on right here because you see this amazing convergence going on and a lot of little little vortices that kind of merge with the tornado. And you can see that, and you also start to see these positively buoyant surges in the RFD. So a lot of research is going on in these secondary RFD surges. There's probably tertiary ones, and whatever goes after tertiary, I don't know, but there's a lot of them. Here's another one. It's very unsteady and very turbulent. Whereas over here, it's a bit more smooth and laminar. So there's different kind of scales of motion going on here. Now what you're seeing is the tornado is undergoing what's called vortex breakdown. And I was really happy to see this because this is something that has been seen in tornado models and in laboratory studies. So here's just a snapshot of the tornado at this time. You can kind of go up and see what's going on. It looks kind of like a pretzel. You have two sort of intertwined cyclonic vortices, and in between that is a downdraft. Okay? And if you look up the two-celled model of tornadoes, you'll see it looks really good. I mean, it looks like we're capturing this pretty well. So I'll let this go for more. There's another positively buoyant surge in the cold pool in the RFD region, more of these vortex mergers. A lot of very turbulent flow here in the RFD. And as you'll see when I start dropping trajectories, a lot of this air gets into the sort of outer outer reaches of the tornado cyclone. And that little anticyclonic guy comes and goes, and we'll watch as this sort of consolidates some anticyclonic vorticity. And this is that sort of disruptive event that I was talking about earlier. So just kind of, this thing's kind of going on, and then I'm going to freeze it, and I'm going to walk really slowly. It's only going to be 6 times real time. So watch what happens to this anticyclonic vortex as it interacts with the tornado. You can see this is a little surge going on here. So I'll step through it step by step, and it's going to sort of, it's just really incredible, but it's very complex. So watch it as it goes. This is the point at which the EF5 starts to really, it gets a bit weaker. So it kind of scoots around, it's being caught, swept into the circulation. There's even one cyclonic guy that gets swept around the anticyclonic guy, which then gets swept around the big tornado, which has a little vortex around it, which turns and tilts and gets lifted up. I mean, it's amazing. It's really, it's hard to explain this in words. I would just like to submit this to a journal and say, hey. I'm not turn this into words, it's right here. So here's that disruptive event, right? And you can see the evidence in the pressure field of that anticyclonic vortex. So, it actually gets, it never really recovers from that. I mean, it's still a pretty strong tornado. We still have EF5, EF4 winds for sure. Notice now it almost looks like it's a rather tranquil. I mean, it's smoother. I mean, it's still grinding away, but it's not as turbulent. Then the RFD says, well, enough of that. Blasts some more vorticity. Now look at the tornado. I mean, is there a tornado in there? Let's take a look. It looks like a plate of phosphorescent spaghetti, sort of. But yeah, I mean, seriously, we're resolving all turbulence. I mean, it becomes a really difficult, it's really hard again to sort of look at what's going on. But I think we can sort of step back from the detail and look at the real important features, and I think that's the approach we're going to be using. So sure, this tornado gets a little bit funkier for a while. Notice the RFD is now almost positively buoyant over a large region. There's a lot of interesting morphologies going on in the cold pool. I'll also be focusing on these secondary forward flank downdraft boundaries, because over here we're typically used to seeing these diffuse boundaries over here. And we'll look at the secondary. So here's the tornado, using vapor this time, just watching it crank around. We're coming up to that disruptive event. There it is right there. You see a horizontal vortex go up along the tornado. I've seen that in the field, or I've seen other people's YouTube videos of the field. I haven't chased much, but so, and it just kind of goes along. You see a lot of, again, subtornadic flow. You'll see the tornado kind of do things. Again, this is running really fast. This is 60 times real time, so 1 second is 1 minute. And you notice how, you see a lot of evidence. There's a multiple vortex event right there. The tornado lifts. If you look at the surface winds during this point, there are times when you might actually argue that the tornado lifted and a new tornado formed, but it's really all part of the same circulation. But you would see sort of a gap in the damage path, I think, towards the end. So now I'm going to focus on the pressure field. This is the minus 15 millibar pressure deficit. So clearly, tornadoes are regions of low pressure. You can see the tornado. But I'm really interested in this thing here. Now, one thing I want to get across right away is this pulsing nature that you see here has to do with, I believe, gravity waves reflecting off the top of the model. So I'm not entirely sure that's a physical thing, but it doesn't really affect the results. So this thing here, I mean, we're talking about, very, very strong horizontal pressure gradients. I'll be focusing on that in a bit. Now, how tall is the tornado? In the pressure field here, I chose a relatively arbitrary isosurface. You can see it extending up to about 10 kilometers. But if you look at the vorticity field, this tornado extends up to 18 kilometers. I mean, essentially, it goes up to the top of the model domain. That's an important result, I think. A lot of previous work with tornado modeling, you don't see it extending that high. So here's just a snapshot of the cold pool showing some of that interesting structure. The forward flank downdraft boundary, you notice how it's diffuse, but then you see these 1, 2, 3, 4 secondary boundaries. Here's positively buoyant RFD air, here's the anticyclonic vortex, and here's a tornado. So let's focus on genesis. This is just looking at vorticity. A lot of these guys, these are little mesocyclones, and this is the SVC, the Streamwise vorticity current, we're calling it. So genesis, if I just had to use a word to describe it, it's about consolidation. It's about convergence and consolidation of vorticity. And again, we haven't done enough real analysis yet. I did want to check if this SVC is associated with low pressure. And indeed, before you even see a tornado, this region that's sort of saturated is low pressure. So I presume there's an element of cyclostrophic pressure drop going on in the SVC itself, which sort of acts like a tornado on its side, but not really. This is during the maintenance phase when it's really cranking along. You still see this SVC, the tornadoes, the RFD's kicking up all this turbulent flow. But this just, just grinds along for almost, 40, 45 minutes. It's not steady state, but it's relatively steady. Here's a view of the mesocyclone. I'm just looking at W now. So this is the mesocyclone. We're looking towards the east. This is the RFD, and you can see the signature of the tornado in the W field here. Interesting how it's kind of tilted. Here's the view from the south. So this is the mothership view where you just see this giant barrel mesocyclone. And here's the SVC coming in and the tail cloud, and then there's the tornado starts. So I'm really interested in trying all these different techniques. Now here's what I'm doing. I'm dropping a bunch of parcels from right near the ground. I'm coloring them by the actual magnitude of the wind speed. So interestingly enough, the strongest winds are associated with that low pressure lobe. This is the forward flank downdraft boundary here. So behind that is where you see the strongest surface winds. This is the RFD over here. And you can see that this really does look like a gust front. It has the classic structure, whereas the forward flank, I won't call this a gust front at all. It's more of a convergence zone. You can see the tornado forming. And I'll run it a little slower this time. There's that anticyclonic eye. So the blues here are relatively weak winds, relatively, of course. And of course, you see the color map getting stronger in stronger velocities because this is the updraft, very strong updraft. And round and round she goes. The SVC is behind this, so you see sort of a splitting of the flow where you have the tornadic flow here, and over here you have this, again, we're just going to call it the SVC for now. We haven't really analyzed it a whole lot, but it's another kind of a circulation. It seems to be feeding the tornado cyclone aloft, or the mesocyclone, not directly feeding the tornado. They tend to be decoupled. You tend to see them separated by about anywhere from 500 meters to a kilometer. So I'll let this one run one more time. So again, these parcels are right above the surface. And if there's any one thing I could say about what I've heard from other talks in this conference is the winds near the ground are really, really fast in these tornadic storms. And I think in order to properly include the effects of surface friction, we're going to have to run it at terribly high resolution near the ground. This is a free slip circuit simulation. So we have no friction at the surface, which I think is actually, I'm coming to come around to think that this is a good way to go for at least at this resolution. So here's the during maintenance and strengthening, the same vorticity magnitude plot. So you're seeing, there's this horizontal vortex that just gets blasted up and tilted and gets fed into the mesocyclone. It's pretty complex. Again, I think you can get sort of blinded by the details. Now I'm going to be dropping 3 different trajectory locations. This is the RFD region. This is sort of in between the RFD and the FFD region, and this is the SVC. So you can see a couple of things come out. First of all, this Streamwise vorticity current really does look like a coherent flow structure. I mean, the parcels kind of stay together. It looks like a ribbon, sort of. Another thing to notice is that the air that feeds the center of the tornado around the downdraft, so if you think of the core of the tornado has a downdraft because it's two-celled, outside of that region, it's like an onion, where that air is really coming from the cold side. I'm going to drop some parcels right here on the warm side in this notch here, and it's interesting because really I'm coming to the conclusion in this simulation that most of the air that feeds the tornado at low levels is coming from the cold side. So the updraft is having to lift cold air, but when you have a really strong updraft and the air isn't too cold, this isn't such a challenge to the storm. And in fact, the advantage is it gets to basically pick up a lot of vorticity. So here's another view of the same set of trajectories. Just to sort of give you another perspective, here's the SVC, here's the cold pool, and here's the RFD region. And again, notice how these guys are separate. They're not this isn't just like getting immediately absorbed into the tornadic circulation. It's more accurate to say that it's contributing a vertical vorticity to the mesocyclone or the tornado cyclone. It's really hard to say where the tornado stops and the mesocyclone begins when you start looking at these high-resolution simulations. The mesocyclone doesn't have that really nice rotational signature that gets implied on radar when you get looking at it in really high details. It's much more involved in that. Again, here's a view from the ground. We're from the south looking north. Notice the RFD air does indeed feed the tornado, but I would say that the RFD air, as it surges forward, it's sort of like one of the outer rings of the onion. It's not one of the inner rings of the onion. Notice how the yellow parcels, they mix and stuff, but I would say it's more accurate to say the RFD air feeds the tornado cyclone more than it feeds the tornado where the winds are the strongest. So here's where I drop some of these white guys on the warm side. And it's really interesting because some of these guys feed the outer tornado and some of them slide over to the SVC. You'll see as the simulation carries on, but you'll see some of these white parcels coming over to one side, feeding the SVC, and some of them are feeding the tornado cyclone. So I'm not really sure what to make out of this yet. There's a lot of analysis we need to do. And I'm not saying for sure that there's no warm air that gets into the tornado because I'm not ready to say that, but it does seem that the tornado is fed primarily by cold, cool air at low levels. Here's where I just turn on the vorticity in case you didn't realize there was a tornado here. You can see the vorticity field. But anyway, and here's your anticyclonic guy over here. Incidentally, these parcels are being calculated by the vapor software, whereas the vorticity is a field drop by CM1. I'm very, very happy with how these two things agree. In other words, the vapor software is integrating the trajectories and doing a very good job. So here's the SVC. This is just vorticity magnitude. This one runs for a long time, so what I'd like you to pay attention to is how this, essentially, the magnitude of vorticity sort of waxes and wanes. So for a while, the SVC just basically goes away. Now again, it's an arbitrary threshold I'm using for vorticity, but it goes away and the tornado kind of doesn't get it's not as turbulent. And then, bam, you get this big RFD surge, and you see all this vorticity getting swept into the tornado. And right after that, you see the SVC sort of kick in again. So there's these sort of long period oscillations that are going on in the storm. I'm nowhere near the point where I can talk about causality here, but you know, it's not a straightforward circulation. It does change over time. Thankfully, though, there are periods in the simulation where things don't change too much over time that we might be able to come up with some conceptual models about what the flow is doing while it's relatively steady. Here's again another view of the SVC. We're looking from the cold side towards the south, looking south. I like this view. Some of this sequence shows absolutely unmistakable evidence of rotation. You see all these globs of vorticity are just turning. I mean, it just really looks very, very convincing there. Here's another run of that sequence there showing that rotation there. So now it's not news that low-level baroclinically generated horizontal vorticity feeds or is responsible for low-level rotation in the mesocycle. That's not a new result, but this is a mechanism that I don't think has been seen before, at least in this detail. Here's my favorite view, just looking down that boundary. I don't know, it's really amazing. I'll run this one twice and I'll run it back and forth a little bit, I think. So, you know, it's, again, I can describe this with words, but this really tells a good story. And this is one of my main goals, is to make do a lot of work like this, because these storms, there's aspects of these storms that it's really almost impossible to describe without really showing this kind of thing. It really tells a good story. So this is this is definitely contributing towards the mesocyclone rotation in the vertical. So this is horizontal vorticity that's being tilted into the vertical, and it has to be getting stretched because it's entering air that's moving faster. I'm going to probably have to do some analysis using maybe natural coordinates to see what's going on with this air, but lots of analysis to be done on this storm. So right now, I'm at a phase where I can crank out these movies pretty quickly. I wanted to look at a period where that SVC was weak to see what the circulation is here. And it's essentially the same flow regime, only not as dramatic. The updraft isn't lifting this air up more down towards the forward flank like it is right here, for instance. Here's another view of the SVC. And I mean, you can't get vorticity more streamwise than this. I mean, it really is flowing right along. The motion of the wind and the vorticity, those vectors are aligned very, very well. So it's a very efficient mechanism. This storm has come up with a very efficient mechanism for creating vorticity in the vertical. So here's your sort of day-glow tornado. This is I'm going to focus now on the decay phase of the storm. Again, you're going to see the pulsing, but what I want you to notice is how quickly this thing dies. This does not get undercut by cold air and go into this nice photogenic rope stage. It just goes almost along its length. So both the genesis phase and the decay phase, I wouldn't call it simultaneous, but it seems like the tornado is pretty much, there's some sort of communication or something going on along the tornado where it is pretty much forming and decaying at the same time at different levels. And this is, I'm thinking of, again, Jana Hauser's talk at the SLS conference where she noticed that also in radar data where you saw the different levels pretty much showing at the same time. Here's the vorticity field, boom, it's gone. Okay, now again, 1 second of our time is 1 minute of the model. So, but it dies in about a minute. And I'm just going rocking back and forth here. So decay, so I've got all three things. I've got genesis, maintenance, and decay. All three things are important to us. And this one surprised me. Here's these wind vectors at 500 meters, again showing the updraft. So you'll notice that blues start to really dominate as this thing croaks. And essentially, I call it death by downdraft. It really does get sort of consumed with this. I'm not sure yet whether the downdraft is forced by, say, precipitation drag or negative buoyancy, or if it's nonlinear vertical hydrostatic pressure forces that I think are probably very important. So, I'm going to have to do that analysis, but at least it's a pretty clear picture. And when this thing dies, it's a storm after my own heart because I studied downbursts for my PhD. It's like death by downburst. But yeah, you see a really strong downburst occurring right at the end. It's as if this tornado is holding on for its dear life, and it's like, I'm gonna go out in a blaze of glory, and it does. It's as if the regime that was in place, keeping this thing steady, just falls apart. And it is getting highly occluded at this point, okay? You see the tornado is really behind it. So there again, and you can see so warm air here is probably being produced by adiabatic compression. Again, I haven't looked into it yet, but when you see a downdraft like that, it certainly gives you that idea. And the SVC is much weaker at this point, and the cold pool is getting warmer. So when you see these warm colors, this is air that's actually positively buoyant. So that's kind of interesting. So I'm coming to the end, or coming to the close pretty soon. The next sequence I'll show you will show the rain field along with the tornado, and you'll be able to see how the precipitation field affects. So this is the model resolution, by the way. You're seeing every grid point. I wanted to show some slides. So here is rain. Rain, and this is pressure deficit with the isosurfaces. So I'll run it at regular speed first, but notice how it gets really enveloped by rain. Poof, it gets kind of stomped on. And I'll do it a lot slower for the next sequence. These are separated by 2 seconds. So the tornado, and it's been wrapped in rain for a long time, but these are very high mixing ratio values. So it's really rainy, and then watch, it just kind of falls apart in like half a minute, and then forms this tiny microburst, very intense winds, and then it's all over. And it never comes back. I ran it for another 15 minutes or so just to see if it was going to cycle or whatnot, but no, it doesn't. So I don't have a conclusion slide. I'm a little light on scientific conclusions at this point. That's why I'm making all these really awesome movies, because it helps me see what's going on and sort of try to form a story in my head. And we haven't published this yet, so that's obviously a high priority. But anyway, thank you very much for your time, and I've got a couple minutes left for questions.
Lee, if I understood your SVC right, so that's where you're getting the bare clinically generated vorticity, and when it sort of disappears for those periods, does that mean what you're finding is the temperatures for some reason are not as cold in the cold pool? I'm trying to figure out what would cause the baryclinic vorticity to pulse that way, to sort of cycle down and then cycle back up, because you picture it's still raining a lot, creating the cold pool. And yeah, so have you got a chance to look to see why the SVC pulses that way?
No, and I have a feeling it has a lot to do with microphysics, which is always, wow. When you look at the structure of the cold pool structure plays a huge role in this. I think what happens is you just stop getting those intermediate boundaries, but honestly, I don't know the answer to that question, and that's one of the main questions we're trying to figure out, but it's definitely something that's on our radar to look at. Yeah.
I was noticing the streamers that came off of the you're playing downdraft, and you had them go off a lot further aloft, most of them go up and then kind of mix with the vortex aloft. Is there something that happens to the mesocycle aloft? A lot of those streamers, a lot of those tracers from the RFD go way up aloft and then kind of mix with the vortex?
Yeah, so you get these pulses. You get these pulses in the RFD. They, of course, can generate horizontal vorticity. And then some of that air just gets lifted. Once one side of that vortex gets lifted, it gets sucked into the updraft. So I don't know. I mean, there's a lot of models out there already for the role of the RFD versus the FFD and such. So far, I've been focusing more on the FFD because I'm convinced that that's a key for the longevity of the storm. There's just so much to look at. But clearly, the RFD is providing some vorticity for the, again, you've got these creating horizontal vorticity, convergence, and you have lifting, and obviously you're going to have some stretching as well. But no, the actual role of that, I'm not sure. There's just so much to look at. I've got 100 terabytes of data to look at. So.
I just thought it was interesting because you showed a lot of it. I was wondering what it might do to the mid-level mesocycle.
Right.
Low-level mesocycle.
Absolutely.
If you had it go up, you had a little bit going to the vortex, but a lot of it go up towards the meso.
Yes. I know.
That was crazy.
It's crazy because, trying to map, we've got these conceptual models and then we have this ridiculously high resolution stuff and it's just difficult to untangle everything. I've only been looking into the bottom 6 kilometers for most of these renderings.
Okay.
So we have, we're going to be looking at that, definitely.
I gotcha.
Yep, absolutely.
Okay, we've got time for one more question.
Have you done any kind of comparison with the observations from, say, like Vortex 2 versus what your computer modeling has shown? And you kind of say, okay, here's what's been observed, and how do they compare?
Not yet. The reason partly is because I'm chair of the department. I don't have, my research is taking off, and I've been frustrated by the fact I haven't been able to dedicate enough time. So no, but obviously, I'm really interested. I keep mentioning Jana Hauser. I hope she doesn't throw anything at me for mentioning her name so much, but she actually has Raxpol data of the 24 May 2011 storm. And I'm not claiming to simulate that storm. I would never do that, but there's a lot of similarities. So that's one storm, one data set I'm interested in comparing to, but there's just a lot of other stuff out there. And obviously, when we start really grinding through the analysis, we'll be comparing the field observations.
Okay, outstanding, Lee. Thank you again, and let's thank you.